Okay, our first class is for the issues of numbers. Physics deals with numbers as well as in mathematics. However, in mathematics, any number is dimensionless. In physics, some numbers are dimensionless, but some numbers are dimensionful. That is the most complicated case in comparison with the mathematics. As a simple example, we consider a sinusoidal function called sine of x. In mathematics, from middle school, you learn sine of x and cosine of x. And when you deal with sine of x, we assume x is a number. Especially, it can be extended to any real number. If you learn complex variable, this x can be extended to a complex number, but we are not interested in the complex number case in this class. Anyway, sine of x has its argument x that is a real number. You know, real number consists of rational number and irrational number. For example, square root of 2 is an irrational number, and 1/2 is a rational number. Rational number is a number that can be expressed in terms of a ratio of two integers. By the way, sine of x is actually for a triangle. Let us draw a triangle. Now, right triangle, for example, we have r, x, y, and the angle theta is given in here. In that case, what is the sine of x, sine of theta? This is, everybody knows, y over r. And what is cosine? X over r. As you can see, x and y are both of dimensions of length. This one is length, this one is length, this one is length. It has a physical scale of length. And we can see this sine is a ratio of length. In addition, the argument theta, here x, is different from this side length x. Theta is the angle that is defined, usually conveniently defined by a circle. You have radius r, and this is theta. And this is a sector whose arc length is L, and everybody knows that the ratio of this arc length relative to the radius r is the angle. Again, just like the value of sine or cosine, this argument theta is the ratio. In this ratio, length over length, length scale cancels exactly. Therefore, angle is dimensionless. In mathematics, they usually write sine of x, and x is a real number. However, in physics, we usually use x for a position vector or displacement, something like that. So x in physics is usually dimension full, and its dimensions are length. That is the main issue. Sine of x has an argument. This is a pure number. Pure number means it does not have any dimensions. So When you make use of any mathematical functions in physics, you should be very, very careful about the dimensions. The number in physics always carries its own physical unit that has physical dimensions. Next, we consider variable. What is the difference between physics and mathematics in variables? In mathematics, unknown is usually written as x, and in physics, we usually write x as a position or displacement, v as velocity, a for the acceleration, capital F for the force, tau for the torque, and so on. All of the letters that represent a physical, measurable, a quantity that can be measured physically, or quantity, is expressed as italic letter. Italic, it is not Roman. These are Roman, and these are italic. Italic letter represent a physical variable. Any italic letter appearing in mathematical expression is dimensionless pure number. Any such letter in italic form appearing in physics expression is not a pure number in general. It may have its own dimensions. Be careful. In both mathematics and physics, we use some array of numbers that are called a matrix. And when a matrix is collapsed into a single column or row, we usually say it's a vector. So a vector is a special form of a matrix. In any case, an element of a matrix is eventually a number. Usually in mathematics, they say field on which the algebra is defined. However, in physics, field means a different one. In physics, field is a function of position, sometimes a function of time too. For example, if we put E in here, then electric field, that is a function of position and time. So field in physics is different from mathematical field. As I already told you, we always use italic letter to represent a physical quantity, and that is in general not a pure number. It contains its own physical unit. Next, we consider dimension. In mathematics, you are acquainted with the one dimension, two dimensions, and three dimensions. You are very familiar with the number line. This number line represents a one-dimensional Euclidean space on a straight line. We will usually use a real number to represent any point on a number line. And mathematicians are interested in whether the point represented by a real number is rational or irrational. However, physicists are not so much interested in whether the number is rational or irrational. It exists, that's it, and we can improve our expression as much as possible to reach the real value, real physical value. So we are interested in real number, that's it. The dimension is quite important in that what is the number of independent parameter to represent a system completely without missing any point. A number line of any point can be represented by a real number x as long as you choose 2 points. One point is the reference point that is called the origin. And you must define where the unity is. So 1, 0 are defined. From then on, you can choose any point P, and that point is expressed as the displacement from 0 to that point and relative to the distance from 0 to 1. So that's the reason why we need only a single number x to represent a single point in one-dimensional Euclidean space. However, if you extend our space into 2 dimensions, as you learned from middle school on, you can introduce x and y axis on the plane. And you choose 0, that is the origin. After that, whatever point you may choose, you can find the projection onto the x-axis and another projection onto the y-axis, and we assume they are orthogonal, that they're perpendicular to each other, and find out the coordinate along the x-axis and the y-coordinate along the y-axis. This is a great triumph introduced by Descartes. And Euclidean geometry is completely expressed in terms of Cartesian coordinate. The Cartesian is the adjective representing Descartes. Because of the Descartes' work on this representation of any point in Euclidean space, Euclidean geometry can be solvable using algebra. And sometimes we can extend it by developing calculus developed by the physicists called Newton and Leibniz independently. Calculus was not developed by mathematicians, even though you learn from mathematicians. Its origin is physics. It is not mathematics. So how many independent parameters is necessary to describe a system? Only a single? Then it is a one dimension. We have 2 coordinates, so we have 2 independent parameters to represent a single point on the plane, so we have 2 dimensions. Unlike a point on a straight line, the motion from a origin, a certain point, to another may have various kinds of path. So this is a big difference between the single dimension and 2 dimensions. In addition, if we can extend this one into 3 dimensions, we can introduce 3 Cartesian coordinates X, Y, Z axis, and it's a projection. For example, if I choose a single point, it's a projection onto the X axis and Y axis and Z axis. It will give the coordinates X, Y, and Z, and we can express this point in this linear combination. Linear combination means we have a certain vector that represent the direction, three independent direction that are called the basis, and the coefficients that are usually a real number in mathematics. However, in physics, this unit vector is dimensionless and the length dimension is fully carried by the coordinates. As a result, the necessary number of parameters to represent the system or point in physics is in mathematics is called a dimension. So in two dimensions, we have two coordinates, and they are the the coefficients of basis vectors that represent unit basis vector along the x-axis and y-axis. They are perpendicular to each other. Because they are perpendicular to each other, they become a zero at the origin if and only if the both coefficients vanish. So this is, we call this the linearly independence of the basis vector. Only if we express a position of a vector or position point in terms of linearly independent elements called the basis, the coordinates are uniquely defined. The reason is that zero is unique. You might have learned in mathematics class already. What are the dimensions in physics? Dimensions in physics is much more complicated than the dimensions in mathematics. The reason is that physics deals with nature, and nature is not a number at all. It has a property that has similar property as numbers. However, nature is not a number. Physics deals with nature. Mathematics does not deal with nature. Mathematics is human imagination that is perfect. The dimension, first of all, mathematical dimension is included in physical dimensions. For example, these Euclidean space for the one-dimensional and two-dimensional, three-dimensional Euclidean space. When you learn this Euclidean space in mathematics, you forgot about any dimensions of length. Here, this straight line, distance of the 2 points should be defined. Distance is not 1 at all. Distance should be 1 meter or centimeter. It has a unit whose physical dimension is a length. The plane, for example, you consider a rectangle. Rectangle has an area. Area has the physical dimensions of length squared. What about the volume of a cube in three-dimensional space? You need to write length cube to represent the physical dimensions. That's not all. Physics deals with nature. Nature It consists of space. Space has three dimensions. Dimension Q. Time. Without time, we cannot describe the motion. Time is another dimension in physics. In addition, this is empty space. Nature is not empty at all. Matter fills the space and time, and matter has its own basic property called mass. So fundamental dimensions of physics consist of powers of length, mass, and time. Now, let us return to a simple algebra. If you learn number, you are interested in carrying out an operation. In elementary school, you learn how to add two numbers, then subtract, then multiply, then divide. So we say in mathematics, it's algebra, plus minus times division. Whatever number you bring here, we can add the two numbers as far as they are real numbers. However, in physics, if you bring two physical quantities, it is not always possible to construct an algebra. For example, 1 centimeter stick and 1 gram of water. Can you say 1 plus 1 equals 2? Stupid. Impossible. Impossible. The only case when we can add two numbers in physics, it is not mathematics, only if their physical dimensions are the same, and perhaps we can introduce a single unit system, then both the lengths can be expressed in terms of a single unit, then this single unit is factorized, and you can add these two numbers to find out the answer. Therefore, you should be very careful about the hidden physical dimension represented by any physical quantity expressed in terms of italic letter. There is another way of classifying physical quantities, that is scalar, pseudoscalar, vector, and axial vector. In addition, we have tensors. Scalar is, for example, a real number can be assumed to be a scalar. Actually, a vector, you are familiar with the displacement x in the three-dimensional space, that is a vector. The origin of a vector is not coming from mathematics textbook, just displacement. Carbon copy of the displacement into a very, very abstract form is called the vector. So vector did not give birth to the displacement. Actually, the displacement is the origin of a vector. Displacement, sure, Euclidean geometry is the origin, okay? Because our Newtonian mechanics assumes that space is Euclidean. Sure, it eventually proved to be wrong in the case if you are running very, very fast, or if you are going into very, very tiny space, where a single electron or smaller object is living in, the Newtonian mechanics and the Euclidean geometry breaks down completely. So although mathematician can travel to the world to the infinity or infinitesimally small space arbitrarily, it's their own freedom because it's human's creation. Mathematics is human's creation. If you really reach a very tiny space, Euclidean space breaks down. If you fly very fast, like just speed of light, Euclidean geometry is not correct anymore. So we should be very careful in applying mathematical theory to physical situation. Anyway, scalar is similar to a real number. It has only single direction, go forward or backward. That's it. However, from dimension 2 on, there are various directions allowed. So as well as the magnitude of vector has its own direction. Because of the direction, for example, if you rotate a point on a circle, coordinate x comma y, they vary depending on the angle. You know, it is a radius, then r cosine, and this is r sine. So any Cartesian components of a vector, this is a vector, any Cartesian component of a vector vary depending on the angle on the rotation. So this systematic change of coordinate is called covariant. It varies, but it has a systematic rule to have such a transformation. So on the rotation, a vector has a special rule of changing its own coordinates. So scalar does not change it. For example, radius does not change. So scalar can be understood as a one-dimensional vector. However, there is another classification. When you learn mathematics, any function can be expressed as a linear combination of even function and odd function. Even function does not change its own shape after reflection against y-axis. However, an odd function flips its sign if you exchange the left and right. So similarly, any vector transformation into negative value is called parity. On the parity, a vector transforms into negative value of its own vector. However, there is strange vector such as angular momentum that follows exactly the same covariant rule like a vector in that its coordinates transforms in this way, covariantly. However, if you apply this simple reflection that is called the parity, negative sign appears twice. So this angular momentum does not change its own value. It is invariant under parity transformation. So this kind of special vector is called axial vector. In a similar manner, for example, x dot x, this scalar product of two vectors is always a scalar. However, we can also make a scalar by making a triple scalar product of the three vectors. In that case, on the parity, it changes the sign because there are odd number of vectors. Our result on the parity is negative. So such kind of scalar, even though on the rotation it does not change its own value, it flips the sign on the parity. We call it pseudo-scalar. So this is another classification of a physical quantity. It is possible to bring many vectors as a product. In some case, we have tensor. And for example, electric field has the three Cartesian components, and magnetic field has the three Cartesian components. So electromagnetic field is expressed in terms of 6 Cartesian components of electric and magnetic field. However, it is now understood as 6 independent components of a 4x4 matrix that is called the field strength tensor. Such kind of one is called the tensor, the product of vectors.